Continuing our discussion of magnetic forces, we're going to move beyond how they affect individual charges and instead see how they affect groups of flowing charges and current-carrying wires. So let's return to the scenario that we saw previously. We have a very big magnet with a magnetic field going from the North Pole to the South Pole, so directed downward, and we have a charge moving perpendicular to this field. And we already saw in the previous video that when this occurs, this charge will experience a magnetic force that is perpendicular to both the motion of the charge and the direction of the magnetic field, so something along these lines. In this particular situation, it would be directed out of the page. But what if we had more than one charge immersed in this field? Well, if they were all moving together with identical velocities or near identical velocities, well, then they are all going to experience similar magnetic forces perpendicular to both their movement and the magnetic field. Well, what do we call a flow of moving charges like this? Well, it's a current, and typically we can think about these as being immersed in a wire. So the wire itself would experience this magnetic force as the current flows through it. So the conclusion from what we just saw is that a wire carrying an electric current experiences a magnetic force if it is positioned so that the current is running perpendicular to the magnetic field. So much like charges, it must be aligned in a particular direction. Now, a couple things here. If we have no current in the wire, well, then there's no flowing charges and there's going to be no magnetic force. And additionally, if the wire is positioned so it's running parallel to the field, well, the charges would be moving parallel to the field. Once again, no force. And we also have to remember that the magnetic force on the wire is in this third dimension. So if we look at our three dimensions, one will be the current in the wire, one will be the magnetic field B, and the third will be the magnetic force on the wire, so perpendicular to both of those previous two vectors. So let's undergo a pretty simple derivation to figure out what the equation for this force would be. So let's look back at the equation we learned last video, which is Fm, the magnetic force, is equal to the charge times its velocity cross the magnetic field. Now, keep in mind, we also learned QVB sine theta, but we're just going to start with this one and we can kind of extrapolate from there. So we have this here. Well, the definition of velocity is displacement over time. So we can replace V with delta x over delta t. And now we're just going to do a little bit of rearranging. I'm just going to move the delta t from underneath being delta x, because, these are multiplied with q, to underneath the q. This is totally acceptable. So now I have q over delta t times delta x cross b. But what is a charge over time? Well, that is a current. So now I have I times delta x cross b. And lastly, we're going to make one small little substitution, which is instead of saying delta x, I'm going to call this L. And we're going to say that L is specifically the length of wire in the magnetic field, so it's the distance the charges are moving through the wire within the magnetic field. And this gives us our equation on the magnetic force on a current-carrying wire, that Fm is equal to IL cross B, where Fm is the magnetic force in newtons, I is the current in amps, L is the length of wire that is immersed in the magnetic field in meters. Remember, that crosses the cross product, and B is the magnetic field intensity or strength in Teslas. However, this is all well and good, but usually when we're actually doing the math, we don't really think about it like this. Remember, we want to think about the magnitude and the direction. With the magnitude, we just simplify this and make it Fm is equal to ILB sine theta, where that theta is now the angle between the wire and the direction of the magnetic field. Typically, those will always be perfectly perpendicular. They'll be at 90 degrees, so we can just say it's equal to 1, that sine of 90 is 1. But occasionally we might see that that's not the case. Well, what about the direction of the magnetic force on this current-carrying wire? Well, we're going to use the right-hand rule again, and this time it's going to look really familiar because it's pretty much identical to the one we did for moving charges, which is I'm going to arrange my hand in such a way, I'm going to point my thumb in the direction of the current. So instead of being in the direction of the moving charge, this is on the direction of the current. My fingers will be in the direction of the magnetic field, and from there, my palm will be in the direction of the magnetic force. Now, a couple notes. One, obviously, you need to make sure you're using your right hand. If you don't, you're going to be in a lot of trouble. So I, B, and then the magnetic force is in the direction of your palm, in this particular situation coming out of the page. Now we can also, remember, do it like this, where we have our 3 fingers, where we have I is our thumb, the B is our pointer finger, and the magnetic force is our middle finger. I don't care which one you choose. And lastly, one thing we do need to note is that this is only true for conventional currents. So remember what conventional currents means. That's assuming that it's positive charges flowing. And we know that realistically, it's actually negative charges flowing, so you'd have to flip this or use your left hand or whatever. But thankfully for us, we pretty much only deal with conventional currents. So whatever direction the current is saying, that's the direction your thumb goes. We don't need to overcomplicate this. It's going to go from positive to negative. In the circuit, it's going to be the flow of positive charge. So let's look at an example. Let's determine the magnetic force on this length of wire at this moment of time when it's in this magnetic field. Well, if we look, the current in the wire is 4 amps. There are 2 meters within this magnetic field. The magnetic field is 2 meters long, and the magnetic field has a strength of 0.6 Tesla. So I'm going to use my equation. Fm is equal to ILB sine theta, and these are arranged perpendicular. I is going to the right, B is going into the page, and so I'm just going to basically multiply all my factors together, and I'm going to get a force of about 4.8 newtons. All right, well, that's the magnitude, but how do we do the direction? Now, okay. Keep in mind, I'm going to arrange my hand how you should be doing it, so basically do exactly what I'm doing. My body, though, is going to be a little bit in a different position from yours. So I'm going to take my thumb, I'm going to point it to the right, because that's the direction of the current. I'm going to take my fingers, and I'm going to direct it from your perspective into the screen, into the board. And if we can see, that means my palm is going upward, so therefore the force will be directed up. So the total is, the magnetic force is 4.8 newtons up. Well, let's look at a slightly more complicated scenario. Let's consider that we've got 2 current-carrying wires, and these wires carry currents in opposite directions. Wire 1 has 10 amps going down, wire 2 has 8 amps going up, and they are together 1 centimeter apart from each other. And we want to know what's the magnetic force per meter of wire 2 caused by the magnetic field generated by wire 1. Okay, now let's kind of slow down what we mean there. Both of these, when they have currents, will generate magnetic fields. So the question is, when wire 1 generates this magnetic field, it's going to affect wire 2. How does wire 2 experience a force per meter of its length? All right, so let's first off by figuring out, well, what is the size of the magnetic field generated by wire 1? Well, we would use the equation B is equal to mu naught I over 2 pi r, and we would substitute in, we've got mu naught, which is 1.26 times 10 to the minus 6 Tesla's taught amps over meters. We have that the current for wire 1 is 10 amps, and we have that the distance between them, because we're looking specifically for the magnetic field at this point, is 0.01 meters, because that's 1 centimeter. Plug all those in our calculator, and we get a total magnetic field of 2 times 10 to the minus 4 Teslas. Well, what is the direction of this magnetic field? We're going to take our thumb, and we're going to have it go downward for the 10 amp one, and we're going to see that when it comes to the wire 2, that should be directed, it appears to be, from your perspective, out of the page. So we have it coming at wire 2 out of the page. Okay, that's step 1. Step 2, we need to figure out what is the magnetic force on wire 2. So let's use this other equation. Fm is equal to ILB sine theta. Notice I just wrote this as 1 on 2. In other words, the magnetic force of wire 1 on wire 2. And we're going to stick in, okay, now keep in mind, this will be the current of wire 2, which will be 8 amps. The length we were looking for per meter, so we're going to say 1 meter, because that will be the force per 1 meter. And then B will be 2 times 10 to the minus 4 Teslas, and they are perpendicular. So we get a force of 0.0016 newtons per meter of this wire. In other words, if we were looking at 2 meters of wire, we would just multiply it by 2. If we were looking at 3 meters of wire, we would multiply it by 3. Half a meter, multiply it by a half, etc. But what is the direction of this magnetic force? Keep in mind, we're going to use our right hand rule, and I'm going to try my best to make it from your perspective again. So wire 2 has 8 amps of current going up, so I use my thumb for the current. The magnetic field we already determined was out of the page, so it's going to be going out of the screen towards your face from this perspective, and we can see that using my palm, the force should be going to the right. And in fact, that is the case, that it would be 0.0016 newtons per meter to the right. But what would the magnetic force be of wire 2 on wire 1? Well, if we know the magnetic force of wire 1 on wire 2, Newton's third law, we should also know the magnetic force on wire 2 on wire 1, because it's going to be the exact same thing in the opposite direction. And in fact, the answer will be 0.0016 newtons to the left. And this makes sense because how would the calculations change? Well, if I was looking at wire 2, instead of 10 amps in this magnetic field, I would have done 8 amps. The direction would have been the opposite direction. And then when I did here, I would have used 10 amps instead of amps. So I really just flipped the two currents and you get the same magnitude. And the directions will just be opposite of each other. So it works out that the force pair, they're basically, when both have currents running through them, they're pushing each other away in opposite directions. All right, well, let's look at this loop of wire that we've put in this magnetic field. And let's say we connected this loop to a battery so that we would have positive on this and negative on this, and so current runs through in the clockwise direction around the loop. Well, how would this magnetic field affect this loop of wire? Well, let's kind of go one piece at a time. If we look at the left-hand side of the loop, the current would be going upward. The magnetic field is going to the right. So from your perspective, it is going to be, the force will be going into the page, away from your face, so into the screen. So we should be expecting a magnetic force of inward. Now I put X's here because we usually think of those as the backside of the vector, so just to kind of remember what this is. Now here in this particular segment, the current is running parallel to the magnetic field, so that would just be a magnetic force of 0. And then this last part, well, it's going in the opposite direction, so it should have the opposite magnetic force, and if we double checked for our right-hand rule, that would work out, and we get that it's experiencing a magnetic force outward. Well, what is going to happen here then? Well, if this side is going in, and this side is going out, well then the entire loop is actually going to experience a torque along the middle line of this loop, and the whole thing is going to start to rotate. And the loop will in fact begin rotating in this magnetic field. Now this will only happen to a point, because as it's rotating, eventually it's going to get to a point where the currents are in opposite directions, and that's going to cause the whole thing to experience a force in the opposite direction. It's going to rotate back. So this loop would basically be doing this back and forth, back and forth, back and forth, which is not overly useful. But is there a way that we could make this more useful? Alright, so this is going to be a little hard to visualize, so give me a second to try to explain what's going on here. We have this really big magnetic field directed to the left. We have our battery hooked up to our loop of wire. Now, okay, this right here is not the loop. This is, we're going to see in a second what this is. The loop is actually going this way. It's going into the page so we can't see it, so really imagine it going like this, across, and down. But from this perspective, we can't see that, but it's basically going to be going this direction, into the board, over this way, coming out of the board, and then back to this direction. So if I look here, for instance, the current, when we hook this up, at this end of the loop is going to be going into the page, and this end of the loop is going to be coming out of the page. We just saw a second ago, that's going to lead to there being a magnetic force this direction and a magnetic force this direction, that the whole loop will begin to rotate. Okay, well if the whole loop is rotating, let me go ahead and get rid of those for a second just so we can see this. The whole loop is going to rotate until eventually, let me reposition this slightly, you'll notice what we have here is we have two little breaks right here. And now those could either be physical breaks, or we could have inserted like an insulator there rather than a conductor. But the point being that when it happens here, for an instant, there is no current running through the loop. So it's going to stop feeling this force, but it's already going to have been rotating, so its inertia is going to continue that rotation. And it's going to keep going, and we'll notice now the current has been hooked up to the other side, and the whole thing is going to reposition now 180 degrees. And you'd think, okay, well, the currents will be reversed, but now because of this break, well, this side is now the positive, this side is now the negative, and we actually get currents going in this identical direction as they did previously. They experience a magnetic force going that way again, and we have them once again rotate. And when they rotate, they experience that break. The current will therefore go on the opposite side, and once again it keeps going around. This could keep going over and over and over again And so what we've basically formulated here is a DC direct current way of causing this middle piece to rotate continually. And it's actually converting electric energy from the battery into mechanical energy, because I could hook something up this loop and have it do physical mechanical work. Well, what is this? This is actually an electric motor. So an electric motor is a device that converts electrical energy to mechanical energy that has tons of different applications. And ultimately, how it works is we just have current carrying loops of wire that experience a torque because they've been placed in a magnetic field, and they experience those magnetic forces in opposite directions on opposite sides of the loop. Now, these are a couple of examples of what these motors look like. You can see the cross-section of one here. Now, these can either be DC, like what we just described, or they can be AC, where essentially if you have the alterations in current, the reversal in direction at just the right rate as the turning of the loop, you can also get this continual motion. And these are used essentially everywhere. Any device that has any sort of motion from the use of electricity, pretty much going to be using an electric motor. So appliances, this includes your washing machines, your dryers, your dishwashers, anything with a fan, so like a literal fan, or anything that uses a fan to cool things down, like your computer, or anything that uses fans like refrigerators or ventilations, all are using electric motors. You also have electronics. Anything that's causing things to spin, disk drives, and your game systems, or your computers, once again fans, all using these. Any sort of tools, like particularly power tools, drills, screwdrivers, anything that causes that rotation, and even things like electric cars, for instance. Much more complicated ideas of electric motors, but they're all based on this essentially basic idea. So what are our main takeaways for magnetic forces on current carrying wires? Well, one, can we determine when magnetic fields apply magnetic forces to wires? AKA when there's a current and when that current is perpendicular to the magnetic field. Can we determine the magnitude of the magnetic force on a current carrying wire by using Fm is equal to ILB sine theta, and we can determine the direction by using our right hand rule, remembering that our thumb is the direction of the current, our fingers are the direction of the magnetic field, our palm is the direction of the magnetic force. And lastly, can we conceptually describe how an electric motor operates? One, kind of thinking about all the pieces that go into place, but also remembering that at its core, what it's doing is allowing us to transfer electrical energy into mechanical work.